Hi guys. I want to kind of continue the lesson that we had done on Thursday. We talked about the rotation and the revolution of the Earth and the path of the sun and the stars across the sky. This is a very ugly sweater that I think would be an awesome thing to have. The idea that axial tilt is the reason for the season. It's kind of a joke, but there is a scientific explanation for why we have seasons, and we're going to talk about that today in this lesson. So, axial tilt is referring to the tilt of the Earth on its axis. So, I want to kind of put that out there in the beginning, and then I'm going to explain to you the science behind that. It's really important to know what causes seasons. All right, so we're coming back to the solar system scope simulator, which we can use to kind of prove the idea of tilt being the reason for the season. So what I want you to do is kind of imagine here's the Earth, and you'll notice the date is June 21st, 2020. So I fast forwarded a little bit into time, but I want you to imagine if you were to look at the Earth and look at where the North Pole is, the North Pole is right around here. So I'm going to just draw a line kind of going through the Earth. Maybe I'll change the color so you can see that a little bit better. Okay, so you can see this nice line coming out of the North Pole, and we'll draw one coming out of the South Pole down here. So you can see this tilt. There's a tilt of the Earth of about 23.5 degrees here. Now, June 21st, if you notice, this North Pole is kind of tilted toward the sun. So I'm going to just erase that, okay? And you'll notice that like the northern part of the Earth is mostly in sunlight here. I'm going to erase that, I'll clear the screen here. And now what we're going to do is we're just going to fast forward time, and we're just going to speed it up until we get to December 21st. So I'm just going to fast forward, and I want you to notice, okay, so the Earth is spinning, we're going forward in time, and you'll notice that, okay, we're coming into August, and we're getting around to the other side. The Earth is revolving around the sun, okay, and we get around here, and I'm going to stop it right there. Let's set the actual date here. I'll set the actual date to December 21st, so I didn't stop it perfectly. Okay, so now what I want you to notice is, okay, where's the North Pole? I'm going to draw that line again like we had before. Here's the North Pole. You can kind of see Africa there. It's extending out this way, and there's the South Pole extending out this way. Okay, so you can kind of see the North Pole is now pointed away from the sun, and the South Pole is kind of pointed towards it. So it's tilted, if you want to say the northern hemisphere is tilted away from the sun, and that's what causes it to be winter. Okay, the first day of winter is when the Earth is as far away, tilted away from the sun as possible in the northern hemisphere. First day of summer is when the Earth is tilted toward the sun on the opposite side of the revolutionary path. So, coming back to our slides, you'll see that there are two reasons for the seasons, and it was mentioned in that simulator. So the idea that the Earth is tilted on its axis of 23.5 degrees, and the fact that it revolves around the sun once every year. It is not, and this is really key, it is not due to the fact that we might be closer or further away from the sun. It has everything to do with the tilt and the fact that we revolve. Now remember, that tilt is always pointed the same direction. So if you look at this picture here, here is Earth, and you can see it's tilted on its axis. This is June 21st. Notice how it's pointed at Polaris. We've talked about that before. And now on the other side, it's not tilted toward the sun, it's tilted away from the sun, but it's still pointed in the same direction. The Earth is always pointing at Polaris. So sometimes it's tilted toward the sun, and sometimes it's tilted away from the sun. And depending upon the time of year, the fact that we revolve around here, depending upon where we are on this path, that will make different seasons. Okay? Now notice in fall and the autumnal equinox, and in spring, the vernal equinox, it's not really tilted toward the sun or away from the sun. In fact, it's the same everywhere. Okay? So that gives us kind of the in-between stage of things. Now, this kind of goes back to a theory that was put out by a man named Johannes Kepler. And I want to show a really good video that kind of summarizes all this information and does a pretty good job of including some of the things I just talked about in a really nice package. So I'm going to play that video right here.
An astronomer called Johannes Kepler, and how he proved that the planetary orbits are elliptical and that the sun is not at the center of the orbit. It was a big deal when he figured this out several hundred years ago. His discovery solved a lot of mathematical problems that astronomers were having with planetary orbit measurements. While it's true that our orbit's not perfectly circular, those pictures in our science books, on TV, and in the movies give an exaggerated impression of how elongated our orbit is. In fact, Earth's orbit is very nearly a perfect circle. However, because Earth's orbit is technically an ellipse, even though it doesn't look like one, and the Sun isn't quite exactly at the center, it means that our distance from the Sun does change through the year. Aha! So winter happens when the Earth is further away from the Sun. Well, no, not so fast. The Earth is actually closer to the Sun in January than we are in July, by 5 million kilometers. January is smack dab in the middle of the coldest season of the year for those of us up north. Still not convinced? How about this? Summer and winter occur simultaneously on the surface of our planet. When it's winter in Connecticut, it's summer in New Zealand. So if it's not the distance from the Sun, what else could it be? Well, we need to also know that the Earth doesn't sit straight up. It actually tilts. And that axial tilt of the Earth is one of the main reasons for the seasons. The Earth spins on an axis that's tilted 23.5 degrees from vertical. At the same time, the Earth revolves around the Sun with the axis always pointing in the same direction in space. Together with the tilt, the spinning and revolving causes the number of hours of daylight in a region to change as the year goes by, with more hours in summer and fewer in winter. So, when the Sun is shining on the Earth, it warms up. After the Sun sets, it has time to cool down. So in the summer, any location that's about 40 degrees north of the equator, like Hartford, Connecticut, will get 15 hours of daylight each day and 9 hours of darkness. It warms up for longer than it cools. This happens day after day, so there's an overall warming effect. Remember this fact for later. In the winter, the opposite happens. There are many more hours of cooling time than warming time, and day after day, this results in a cooling effect. The interesting thing is, as you move north, the number of daylight hours in summer increases. So Juneau, Alaska would get about 19 hours of daylight on the same summer day that Tallahassee, Florida gets about 14. In fact, in the summertime at the North Pole, the sun never sets. Okay then, it's all about daylight hours. I've got it. Well, no. There's another important piece to this puzzle. If daylight hours were the only thing that determined average temperature, wouldn't the North Pole be the hottest place on Earth in northern summer? Because it receives 24 hours of daylight in the months surrounding the summer solstice. But it's the North Pole. There's still icebergs in the water and snow on the ground. So what's going on? The Earth is a sphere, and so the amount of solar energy an area receives changes based on how high the sun is in the sky, which, as you know, changes during the day between sunrise and sunset. But the maximum height also changes during the year, with the greatest solar height during the summer months and highest of all at noon on the summer solstice, which is June 21st in the northern hemisphere and December 21st in the southern hemisphere. This is because as the Earth revolves, the northern hemisphere ends up tilted away from the sun in the winter and toward the sun in summer, which puts the sun more directly overhead for longer amounts of time. Remember those increased summertime daylight hours? And solar energy per square kilometer increases as the sun gets higher in the sky. So, when the sun's at an angle, the amount of energy delivered to each square of the sunlit area is less. Therefore, even though the North Pole is getting 24 hours of daylight to warm up, the sunlight it receives is very spread out and delivers less energy than a place further south, where the sun is higher in the sky because it's more tilted toward the sun. Besides, the North Pole has a lot to make up for. It was cooling down without any sunlight at all for 6 months straight.
Why are the North and South Poles the coldest places on the Earth? Well, please consider the following. Let's say that this heat lamp is like the sun, because it's hot. And let's say that this globe is like the Earth, because it looks like the Earth. Anyway, we've mounted thermometers on the Earth like this. See? Now, the one at the equator is just about off the scale. And the one at the South Pole is right around the room temperature mark. And the ones in between are somewhere in between. That's because the heat is hitting the one at the equator almost straight on. Whereas at the poles, it's just barely grazing by. And then somewhere in between, well, it's somewhere in between. You see, it's not that the equator is closer to the heat. It's that the heat is hitting it more straight on. See, if the Earth were sitting like this, then this thermometer would be the hottest, and this one would be the coldest. Anyway, that's why the very warmest places on the Earth are right around the equator, tropical rainforests and jungles. And the very coldest places are at the poles, because they're the ones that the energy from the heat lamp just barely grazes by. I mean the energy from the sun. Well, anyway. Thank you for joining me.
All right, so those videos were hopefully informative, but let me just come back to the solar system scope simulator. This is June 21st in our location, so in Syracuse. As you can see, the sun is very high in the sky, which makes the sunlight very intense, which warms up the atmosphere more. The higher the angle of the sun, the higher the altitude of the sun, the more intense the sunlight, the warmer the temperatures. So obviously this is a pretty steep angle. It's about 70 degrees or so, which makes it our first day of summer. Let's change the date just like we've done before. This is December 21st, okay, right there. And you can see the sun is very low in the sky now, so that makes a lower angle, not as intense, not as warm. Now what I want to do is I'm going to go back to June 21st. We're going to go future, okay? But I want to change my location. So right now we're in Syracuse. I'm going to change this. I'm going to move this down to 23.5 degrees north. So I'm just going to make this 30 minutes. Okay. And at 23.5 degrees north, that's called the Tropic of Cancer. And at that location, a really interesting thing happens on this date. So obviously I can't see the sun anywhere. So where in the world is it? Well, you got to look straight up. There it is, directly above you, 90-degree angle. So that makes the sunlight there really intense at the Tropic of Cancer on that day. Okay, now let's change the date. Let's make it December 21st in the same location. And you'll notice that it's much lower in the sky. Okay, so at the Tropic of Cancer on June 21st, it's directly overhead. I'm going to go back to June 21st. And now I want to change my location again. And now we're going to go to the equator, which is 0. And there it is, 0. I'm going to change my minutes to 0. Okay. Just going to hold the button down until it's 0 perfectly. All right. So now we're at the equator perfectly. Now notice, where's the sun? Where's the sun? You can't see it. It's actually over here. Interesting. Okay. And you'll notice that it's lower in the sky on this date. But on the autumnal equinox, which is September 21st, you'll notice it's actually directly overhead. And the same is true on the spring equinox. Right here, it's directly overhead. Okay, so the equator gets the most intense sunlight twice in the year. It's actually always really high in the sky, but on those two dates, it's a 90-degree angle. Okay, now the Tropic of Capricorn, let's change our location. Last thing, Tropic of Capricorn, going down to 23.5 degrees south. And it doesn't matter what our longitude is, as long as our latitude is changing. We're looking for the sun. There it is. It's pretty high in the sky, which makes it pretty intense. Still pretty warm in these locations, but let's just change the date back to December 21st. Okay, that's the first day of our winter, but it's the first day of the Southern Hemisphere summer. And so you can see it's at a 90-degree angle on that day. So just going back to our notes here, this is the Tropic of Cancer, 23.5 degrees north. The sun comes up to the zenith, directly above, and then back down. First day of summer, Northern Hemisphere. Notice all the daylight in the Northern Hemisphere and very little darkness up here, whereas down the Southern Hemisphere, it's a lot more dark. Okay, this is the Tropic of Capricorn on December 21st, kind of the opposite of us. They get their first day of summer directly overhead. Okay, we have more darkness than light. All right, and then here's the equator. Rises perfectly east, sets perfectly west, goes to the zenith on 2 days of the year. The vertical ray is called 90-degree angle, happens twice, and that makes the equator a lot warmer. And all these regions in between the Tropic of Cancer and Capricorn tend to be warmer throughout the entire year because they're getting more intense sunlight. So I just wanted to prove that to you. One other location that was mentioned in the previous video was the North Pole. The sun actually goes around in a circle in the sky on June 21st. Really, it's only about 23.5 degrees above the horizon, so it's not very intense, but it does go around the sky for 24 hours. And then for 24 hours, it's below the horizon. Okay, so kind of an interesting idea there. And by the way, Santa Claus at the North Pole won't see the sun for 6 months. Kind of interesting. Okay, now two more takeaways. Rotation causes the sun to appear across the sky, as well as all the stars. Remember, Polaris is in the middle of this thing. Okay, that's rotation. That's once every day. Okay, rotates once. Revolution causes us to have seasons, but it also causes us to see different stars in the night sky. So sometimes of the year you might know a constellation called Orion. Orion is called the Hunter. Orion looks like this. It's got a belt that is very noticeable. There's 3 stars here. We can only see Orion when it's winter, when we're actually tilted away from the sun, when we're over here in our path, in our revolutionary path. But as we come back around to the other side over here in our swing, here's summer. Now we can't see it anymore because we'd be looking at the sun. That'd be during the day. So you can't see Orion because it's out during the day. Okay. We can see this constellation called Scorpius in the summertime because now we're over here in the path and the dark side would be over here. So we see different constellations in the night sky depending upon when or where we are in this path, okay, depending upon what time of year it is. So that's kind of an important question, is knowing that we see different constellations due to our revolutionary path. So one more thing, just to kind of get into your head. Having the sun go across the sky and the stars go across the sky every day is good proof that the Earth is rotating. But there is a more physical proof that was done by a man named Jean Foucault. And he came up with an idea that if you swing a pendulum back and forth, suspended from the ceiling in a very, very long, long string, and if you swing it back and forth, the Earth is actually rotating underneath of it. And as it rotates underneath of it, it appears that the pendulum actually makes a swinging path that goes all the way around the circle. And you can kind of see that in this picture here. And I'll show you a quick video clip of this. But you can see this pendulum is going back and forth this way. But over time, this whole entire body is rotating counterclockwise. So it looks like it's not doing anything for a few minutes, but over a whole day's time, you'll see that this pendulum will eventually be swinging this way over time, and then this way over time, and then this way over a long time. So over a period of several hours, this will swing back and forth and actually touch every single part of this circle as it swings around the circle. It's kind of hard to see that. This is the actual original Foucault pendulum that was made in Paris. That he went to prove to the scientists that you can prove the Earth rotates this way. And here is a simulation of that. So you can see the Earth is spinning underneath of it. And as it makes a path, it displays this nice green line on the floor. And over time, the Earth is spinning counterclockwise northern hemisphere. Notice that the green lines that are displayed on the ground, if it continued doing this, it would make a complete path around the entire circle, okay? And if you set up some pins on here or something to knock over, it would knock them all over a whole day's time. Okay, so that's the Foucault pendulum. It proves that the Earth rotates. All right, so questions. What evidence indicates that the observer at location A is at the equator? Well, if you remember, the equator has 2 days of the year when the sun reaches the zenith, meaning directly overhead. And you'll notice that in location A, the sun is directly overhead on the equinoxes, March 21st, September 23rd. That's your proof, and you're going to have to know that. The idea that the sun reaches the zenith at the equator twice a year, okay? This can't be the equator. The sun's too low in the sky and it's going around the path. In fact, this is the North Pole, okay? And this can't be it either. And this is probably some location in New York State because the sun is not going directly above this person. Okay, so this is the proof that it goes directly above him on the equinoxes. Explain why the observer's shadow at location B will always point northward at solar noon. Remember, solar noon is when it reaches its highest point. Notice that the sun, in every day here, is always in the southern sky, which means it shines on this person, and their shadow is going to be over here pointing toward the north. That's why, because the sun is always in the southern sky at solar noon. Okay, so this was a question where you had to draw a line to show the path of the sun on August 21st, so you had to kind of interpolate here. So when is August compared to these other dates that are here? So we have June We have September. We know August is in between June and September. So what you have to do is you have to draw a path in between the June path and the September path. And it would fall somewhere in this region right around here. Okay? This last question, how many hours of daylight are seen by the observer at location C on June 21st? Well, notice the sun never goes below the horizon. It just goes in a complete circle path all the way around. So we would have 24 hours of daylight at that location on that day. Okay, so hopefully you guys get the idea about what seasons are all about. And if you have any questions about anything, don't hesitate to ask, okay?